In this lesson, we are going to start to introduce this idea of areas under curves. Eventually, that's going to lead us to Riemann sums. We'll get to that in a different video. But before we do that, let's talk about areas under curves. So if we have some sort of a graph and we have this constant velocity of 60, and it's going to be 60 miles per hour, and we're going for 2 hours, the area under the curve, so if our velocity is 60, from 0 to 2 hours. Our area, we just do an area of this height would be 60, this length would be 2. So we're looking at a 60 times 2, which gives us 120. That 120 has meaning. So this area under a curve has meaning. So for us on this situation, this 60 by 2 is 120, and that 120, if you think about it, we're going 60 miles per hour for 2 hours. We just went 120 miles traveled. So the logic on this tells us 120 miles, but there's also an area under a curve, there's meaning behind it. So if we had some sort of a situation where this graph was a y equals t squared, and that t squared represented something, then when we find this area, there's meaning behind it. So we'll get to the meaning behind it when we get to some kind of word problems, but let's just find the area under it. So if we have a curve, and it's not a geometric shape, it's not a rectangle, it's not a square, it's not a circle, nothing like that, it's a quadratic. Well, I don't have a formula for finding area of a quadratic. So what we could do is kind of parse this into a bunch of different little shapes and then find the areas of the shapes. Now, it's not going to be perfect, but it's going to give us a rough idea, because here's some overestimate, but then here's some under, and then you have some under, and then you have some over. So they kind of counter each other, but it's definitely not going to be perfect. So let's say we take this shape, right, from 0 to 8, and we parse it into 2 individual pieces. Okay, so we're going to make 2 rectangles is what that is. Here we're going to make 4, here we're going to make 8. Right, so if we make 2, and we can decide how we want to kind of figure out these heights associated to it, but those heights end up being a point on the graph because you want it to be as accurate as you can. So on this one, we're kind of finding if you have a distance of 8 and you're going to make it into 2, that means the width of each piece is going to be 4. So if we're going to find our area, we got a 4 by something. So what we need is the height to this. To figure out the height, you could use kind of the left end point of this. You can use the right end point of this rectangle. We're choosing to use the middle. So if we're choosing the middle, how do I find the height to this? Well, if I have a 2, I plug it into this. And so 2 squared is 4. So the width is 4 and the height is 4. So that's the area of that rectangle. This one still has a width of 4. And then its height would be based on 6. And so 6 squared is 36. And so if I multiply those 2 together and add them together, I get an area of 160. But what happens if I were to make it into 4 rectangles? So a little bit smaller, but more of them. And we still kind of are basing our heights on kind of the midpoint here. So we're looking at heights or widths of each of these being 2. Here we would be plugging in 1 to find its height. So 1 squared is 1 plus 2 by, so this one's 2, and then we'd be plugging in 3, which is a height of 9, plus 2 by, we'd be plugging in 5, so 25, and then 2 by 7, which is 49. So again, we have pieces that are missing, we got pieces that are over, they counter each other a little bit, but not perfect. But when I put this into a calculator and add all these pieces together, I multiply them and add them all together, I get an area of 168. I would argue that this area is going to be a more accurate because we have these less overlaps or under pieces, because the smaller you can get, the more accurate this is going to become. So if I do this and I make it into 8 individual little rectangles, then now those little pieces of under and over are even less, play less of a role to this. So it's going to be even more accurate. So on each of these, we're going to make it into 8 rectangles. We divide that out. Each of these widths is going to be a 1. So it's really all the heights, because we're going to be doing a 1 times whatever the height is. Now these heights are going to be these midpoints. So I'm going to be taking a 0.5 and squaring it, which is 0.25. And then I'm going to stop doing 1 times, because really it's just all these different heights. So if I take 1.5 and square it, I get a 2.25. Then if I take 2.5 and square it, I get a 6.25. And each of these would be times widths of 1. So I'm going to drop the 1 on it. And then I would take 3.5 and square it. I would get 12.25. If I take 4.5 and square it, I get a 20.25. And then if I take 5.5 and square it, I get a 30.25. I take a 6.25, I get a 42.25. And then if I take 7.5 and square it, I get a 56.25. So I should have 1, 2, 3, 4, 5, 6, 7, 8 areas of all these individual little rectangles. We add this all together. If I throw this into a calculator, I get an area of 170. So we're getting there, right? If we only do a couple that's quick, but it only gets us a value that is reasonable, and then the smaller, the more of these rectangles I create, the closer we get to the exact area. Now, to get to the exact area is the goal eventually. And so what if I make these things, we make an infinitely narrow rectangle, but we also then have, so it's the width of these become infinitely small, and then we have an infinite amount of rectangles as well. So that would become even more and more and more accurate. And that's our goal. And that's what we're eventually going to try and do, and see if we can figure out a method to make that happen, to get an exact value rather than an approximation.